Okay. Perfect.
Okay. Right. So you already know this publication. And so this is the work I did with Pia when I was doing at Cambridge University. And so if you want to look at the script and data used for that paper, you can access this OSF link. Not sure if you can see my mouse cursor. That's the link if you want to look at the scripts. And I'd like to thank Hui Chen, who is here, and the best who is not here today, but those who helped checking the tutorial scripts for this workshop. So thanks to those two. Okay, so visual word paradigm. So as all of you probably know, in the visual word paradigm, participants look at some object on the screen and listen to sentences. And like I noticed a hungry lion, right? And you can see the lion depicted here, right? And we know that when participants hear those sentences, in the target word, in this case, lion appears, they will quickly look at the object or that's mentioned, right? But people are also sensitive to other relationship between the object and the features of these objects with the target word. So for example, if people hear Africa, they may also look at animals that exist in Africa, or to be more specific, objects that are semantically related to the word that we hear. Right? And that is called the semantic competitor effect. And we can also observe what is called phonological competitor effects. If you hear a word like life, you might also look at the lion because the overlap between life and lion. So these words sound similar, right? And what's cool about this is you can manipulate the overlap between the target and what we call a competitor on different levels, right? So we can use the competitor effect as estimates for semantic or phonological activation by manipulating the overlap, manipulating semantic overlap and phonological overlap. Right. By the way, this is Kabi, who will sometimes appear to assist me during the talk. Okay, so got some example data. So this is a study by Altman and Camille. They asked participants to listen to two types of sentences, like the boy will eat the cake or the boy will move the cake, right? While participants are looking at this scene, right? And the manipulation here is that when you hear the verb eat, because there's only one edible object in the scene, participants tended to look at the cake before the cake was mentioned in the sentence. And when they heard the boy will move, because anything in the picture can be moved by the boy, participants are equally likely to look at the object and didn't show biased looks to the cake before the cake was mentioned. And that's what you can see in this fixation plot. So this is plotting the time from verb onset, so the onset of eat or move, and the y-axis is plotting the probability of fixating the cake or distractants, so other object that's not cake. Right. And what you can see is before the noun onset, so before the onset of the cake, participants are more likely to look at the cake when they had eat compared to when they had move. Right. So we can, for example, use this data to compare likelihood of fixating the cake in the eat condition compared to the move condition. Right. So we're mainly using this fixation data throughout the tutorial and the talk as well. So I'll talk a bit more about this fixation data. So this fixation proportion can be independent, like in the Altman community study. So what I mean by that is if participant is looking at the cake in the boy will eat condition, that doesn't affect the likelihood of the cake being fixated in the move condition, right? Because in this kind of setting, participants only get either of these conditions, right? So they don't hear both versions of boy will eat and the boy will move. And even if they did the comparison between the fixation proportion on the cake in the eat condition and the fixation proportion on the cake on the move condition are independent. We are comparing different trials, right? Compare that with another study where the fixation proportions can be dependent. Okay, so from another study by Alpena, they create a sentence like pick up the beaker, and participants saw the picture of the beaker and the speaker, beetle, and carriage. Right? And when we want to compare fixation proportion to the beaker and speaker or beetle in this setting, right? These are dependent because if you are looking at the beaker you are not looking at the beater at the same time, right? So it's, I mean, at least in the how the eye tracker codes the data, right? There is no possibility for the eye tracker to code. You are looking at both objects at the same time, right? So if you are looking at the beaker, you are inevitably not looking at the speaker at the same time, right? So there is some dependency between the fixation proportion on different objects in this setting. And this is important to keep in mind for the analysis, because in the first case, in that case here, you can compare fixation proportion on the cake in these conditions directly. So by directly, I mean you can run a model like this, where we have a dependent variable fixation proportion predicted by the condition, right, and then plus random effects. But in the second case, we can't run a similar model like this. So we can't run a model where fixation proportion is predicted by different objects, because again, the fixation on different objects are dependent. So there's some relationship between them. Okay. Again, if we want to compare fixation proportion to a beaker versus beater, it violates the assumption of independence, right? LME, for example, the linear model, for example, has the assumption that each observation must be independent from each other, right? So the second analysis would violate such an assumption. So you can't run a model like this. Okay, so that's about visual world paradigm. So let me now turn to the traditional analysis that's been used to analyze the visual world data and how it might be problematic when we want to test the time course effects. So if we want to use, so by traditional analysis, I mean ANOVA or t-test or linear mixed effects models, right? So if we have a data like this, right? So we have time and fixation proportion plotted like in the traditional time course plot, right? And then we see the fixation or proportion on the target increases as the time increases, and the competitor fixation increases and then decreases, right? And the unrelated condition as relatively low throughout the time, right? And if we wanted to compare fixations to the target and competitor and unrelated condition, right, we could run an ANOVA or t-test or LME on the entire data, right? So what we do is to average the fixation proportion across the time course and get data like this, right? So this basically takes all the values from here to here, and then we have the average plotted for each condition, right? Now, this kind of does the job, at least for this data, or at least captures a pattern that the target attracted the most fixation next to the competitor and next to the unrelated condition, right? But by doing so, you also lose some, so yeah, you can test the difference between the condition, but you lose the time course data, right? Because you average across time, right? You end up on one data point per condition, right? So the time information is lost if you do this. So if you wanted to keep the time information, right, what you could do is to run the same model on multiple time windows, right? So, for example, you may decide to run the model in 3 different windows, right, to look at how the difference between the conditions change across time, right? So let's say these are the 3 time windows I want to focus on, and then I'll average the fixation proportion within each window, right? And this might be what you get. So if we do something like this, we can still kind of get a pattern where the difference between these conditions is the largest in the second time window in this case, right? And we can kind of capture something like that. Okay, there's no big difference here, and a bigger difference here, and slightly small difference here, right? So this seems to capture some kind of pattern to some extent. But the problem with this is that it ignores the relationship between the windows that we call autocorrelation. Okay, so in eye tracking data, you typically see a smooth line, right? So it doesn't really see like a shaky line, but it typically goes smooth. And that's because your eyes don't move that quickly, right? Fixations typically last 200 milliseconds or 300 milliseconds, right? So you don't move your eyes that quickly, right? So if you see some pattern at a certain data point, the next data point typically shows a similar pattern to the previous time being, right? And that's called autocorrelation, right? And again, ANOVA or LME assumes that each observation is independent, right? So if there's a correlation between two adjacent observations, that's not great. That's not, the model is ignoring such a relationship, right? And another problem is that, let's say you decide to look at these three windows, but the data may not be that clean. You may not find a difference in the predefined time windows. Okay, so for example, if you had data like this, right, where there's a difference here and not much here, and then here again, but in a different direction, right? And then if you look at the data in the predefined time windows, that's the same windows that we looked at before, then we might end up with something like this, right? But problematic seems to be in window 2, right? So we can see that there's a point in window 2 where the direction of the effect changes, right? But that's not really captured if you look at these windows, right? And you might be thinking that, okay, then how about deciding the windows after we looked at the data, right? It's not deciding which windows to look at before we get the data, but how about we decide after we know that this is a data pattern, right? But if you do that, you could arbitrarily take a window that's likely to find a significance. So this is often called the researcher degrees of freedom. That is, you can choose a window that's kind of best for you, right? So if you find a time that shows something you wanted to find, then it's really tempting for you to take that window, right? But that is what is called researcher's degree of freedom. That is, if you do such a thing, then the results might not really replicate, right? Because you chose the best window for your data, but data, of course, changes every time you run the experiment, right? So it's not really ideal that you take the sort of best window for your data. Okay, then how about this? So how about I run the same model again on multiple time windows, right? So let's say, how about I run 12 statistical models, the same one, to test the effective condition in every window, right? So that I don't have to define which window to look at in advance, right? But I mean, this is probably obvious problem to many of you, I think. But you will then have an increased chance of getting a false positive because of the multiple comparisons, right? And so you are more likely to get a type 1 error. And you can also use a Bonferroni correction to reduce the type 1 error or reduce the rate of false positive. But if you do so, you often lose a statistical power and you're more likely to get a type 2 error, right? That is to conclude that the effect is not significant when there's actually an effect, right? So you ideally want to avoid having a high or too high false positive rate, but also you want to avoid having too high type 2 error rate, right? Or false negative rate. So to sum up, the problem that we want to consider when we look at time course data is the first that the autocorrelational nature should be taken into account, right? So the data point that hasn't been tends to be correlated with the data point in the next time being, right? We also want to avoid selecting time windows arbitrarily. We ideally want to select time window based on our study design and not based on the data, right? We also want to avoid increasing the chance of false positive. Also, we don't want to lose much statistical power and increase chance of false negative. Right? So to deal with these problems, we introduce 5 different approaches today. So the first one is the gross curve analysis, which tests fixation proportion changes over the time course. The second one is a cluster-based permutation analysis, which tests a difference between two conditions. And the third one is a bootstrap difference of time series, which estimates when two conditions differ. And the fourth one, generalized additive modeling, also tests or estimates when two conditions differ. And the final one, the divergence point analysis, tests when the fixation proportion on two objects or two conditions started to differ. Okay. And these approaches don't really solve all the problems. That's why we have different approaches, right? So you need to choose which approach is the best for your research question or design. Okay. Let's now look at different approaches in a bit more detail. So we first look at the growth curve analysis. And these are the differences that you can look at, which are also in the paper. If you wanted to know more about the growth curve analysis. And the advantage of this analysis is that it can analyze changing fixation proportion over time. So, for example, if you have a data like this, right, you can see that the fixation proportion on target keeps increasing, and that to the competitor increases and then decreases, right? And you might want to test at whether fixation proportion on the target increases more quickly than that on the competitor, right? So you might be interested in whether the slope is different between these conditions, right? Or you may be interested in testing when the two fixation curves peak, right? So in this case, we have fixation proportion on two different groups, and you might want to see if the peak for group 1 is earlier than the peak for group 2, right? And the growth curve analysis can test these questions by including a linear term for the first one and a quadratic term for the second one. I'll explain now what the linear term and quadratic term is. So linear and quadratic terms are basically like this. So linear term is basically 1. If you have a 1 to 10 on the x-axis, on the y-axis, you also have 1 to 10, right? And the quadratic is the what is it called? You have a 4 here. It's 4 multiplied by 4. You have that on the quadratic terms, right? This is called natural polynomials. Okay, so linear term and the quadratic terms go like this. But you can see that these are correlated with each other to some extent, right? So if this increases, this also increases, right? So, and that's a problem. So if you wanted to include both the linear and quadratic terms in the same model, that's a problem because you can't really estimate the contribution of the linear term and the quadratic term independently because they are related, right? So what we do to solve that problem is to include orthogonal polynomials instead. Right? So in the orthogonal polynomials, it's just a linear transformation of the natural polynomials here. But you can see that the correlation is reduced in the orthogonal polynomials, right? So we can estimate the contribution of each parameter independently if we use orthogonal polynomials. And this is what we include in the growth curve analysis. Okay, so there's also a disadvantage for the growth curve analysis, that it's not really suitable for analyzing a window with little fixation proportion change over time. And that's actually probably not a big disadvantage probably, because if you do a growth curve analysis, you are interested in how the fixation proportion changes over time. So if your data doesn't have that pattern, you probably don't use growth curve analysis anyways. But if you have such data, the best way is not to include such a window. So when certain windows don't have much fixation proportion change over time, then it's best not to include such a window for the analysis. Another issue is that it might, so it doesn't take into account autocorrelation into account. So autocorrelational nature of the data is not considered by this model. So that may increase the chance of false positive. And another point is that growth curve analysis can include lots of higher order polynomials. So we just talked about linear and quadratic terms, but you can also include linear, quadratic, cubic, and quartic, and so on. So you can practically include as many as you want. And it's not that you should, but you shouldn't actually. But you can include lots of polynomials in your model. But if you do so, it also increases the chance of false positive by overfitting the data. So my advice there would be to include only the polynomials you need in the model. Okay. And so, for example, you can ask yourself if you have a good, very motivated linking hypothesis to include each term, right? So That is, for example, if you want to include a linear term, then you should have some hypothesis about the slope difference between conditions. Right? The second thing you can check is whether the model provides a good fit. Right? So you can, for example, compare the models with and without a higher order polynomial and check which model fits the data better. Right? Okay, and the final thing is that this is something you need to kind of be careful about when running gross curve analysis. That is, a choice of time window sometimes significantly affects the results. Okay, so let's say you have a data like this, right? So you have a time and fixation, and you have different fixation change for group 1 to here, right? And let's say you want to take the entire window for the analysis, right? And if you run cross-curve analysis in this window, you might find interaction of cubic term by group, because the group 2 shows a pattern where the fixation proportion increases, decreases, and then increases again, right? Whereas the group 1 doesn't show such a pattern, right? So you might find such an interaction if you take the entire window. But if you, for example, take a shorter time window, which doesn't include this last bit, right? Then you might find interaction of a quadratic term by group, because here you have a pattern where group 2 shows the increase and the decrease fixation, but it doesn't increase again because we cut this out, right? And if we make the window much shorter, just here, right, then we might find linear term interaction with group, because we now only have the linear pattern, right? We might find that this slope is the slope may be different from group 1 too, right? But we don't have the curvature where it goes up and down anymore, right? So because this is so sensitive to the time window selection, it's best to define the time window for the analysis before you see the data. Right? Again, so that you don't choose the time window, so you find the effect or interaction you want. Right? And I also recommend doing the pre-registration so you can prove that you had to define the time window before you saw the data. Okay, so that's all the description or summary of the gross curve analysis. Let's now look at the example of applying this analysis to real data. So I'm taking the data from my study that I did during my PhD, and this is also a data set we're using for the tutorial. And so I explained the study design a bit, just enough so that you have, you know the conditions and what you need for the analysis. So in this experiment, we had L1 English speakers, L1 Japanese, L2 speakers as participants. So we had two groups, and the experimental sentences were high clause sentences where a certain word was highly predictable, like the tourist expected rain when the sun went behind the, and here the target word cloud was highly predictable based on the context. Okay. And so that was the auditory stimuli. We had visual stimuli that had 4 conditions. So here you can see that only one object was different depending on the condition, right? So the object that was valid was the critical object. In the target condition, you see this predictable words depicted, right? So it's a crowd. And in English compositor condition, you see the phonological compositor of the target. So cloud and crown were phonologically related, right? And in the Japanese compositor condition, the name of this critical object, when it's translated into Japanese, it was phonologically related to the target word. So target word in Japanese was kumo, and the Japanese compositor was kuma in Japanese. So kumo and kuma were phonologically related. Okay. So the predictions of this experiment were that if A1 English speakers predicted this target based on the context, and if the prediction was detailed so that it included phonological information, And I expected that participants will look at the predictable object crowd and its phonological competitor crowd before the target was mentioned in the sentence. Right? If they didn't predict, then the disease effect might occur after the target word. Right? And for the Japanese group, we also expected similar things. But additionally, because of the overlap between the target and Japanese competitor in Japanese, we expected that if everyone Japanese speakers predicted this word, but in Japanese, we might find biased eye movements to this Japanese competitor because of the overlap. Right? And this was the control conditions, our baseline conditions. So we looked at fixation proportion on these objects and compared them with the fixation proportion on this object. Okay. So in this experiment, the fixation proportions were independent from each other because participants only got one of these conditions for each item. Okay, so let's now look at the data for this experiment. Okay, so this is, yes.
Oh, sorry, Janina has a question.
Just a quick question.
Okay, sure.
Was
Yes.
there a behavioral task in this study?
Was there, sorry, what?
A behavioral task? Or they were just...
Yes. Let me think about it. Yes, participants judged whether the sentence mentioned any of the objects depicted. So, yeah, so they had to say yes in the target condition, no in the other conditions. And the yes, no was kind of half 50-50, yeah, overall.
Thank you.
Yeah. Okay, so now it's turn to the data. Also, other people, if you have any questions, please stop me anytime. Okay, so this is the data for the study, now looking at the A1 speakers data and the L2 speakers data. This is now showing the fixation proportion target in red and the English competitor in blue and pink, which mostly overlap with the gray bar. This is Japanese competitor condition, and the unrated is in gray. Okay. So just looking at the pattern, we can see that the fixation proportion to the target increases, right? And this is a target toward onset. So this increase happens before the target toward onset, right? And we can also see that looks to the English competitor happened before the target toward onset. So these looks are both seen predictive. That is happened before the target toward onset, right? For L2 speakers data, we do see like overall similar patterns, but the overall looks to the target seems reduced compared to the A1 speakers. Right, so we do see increased looks at target, and this still happens before the target toward onset. But compared to this data, it seems that the magnitude is a bit reduced. We also do see the English competitor effect, but that happened way after the target toward was mentioned. Right. And there was overall no difference between the Japanese competitor and unrelated condition in either group. Okay. Right, so let's look at whether this data, how we can look at this data or analyze this data using gross curve analysis. Okay, so the data, the model I fitted to this data looks like this. So fix is a fixation dependent variable, right? And 41 and 42 are linear term and quadratic term respectively. Okay, so here I use linear and quadratic terms. And we're looking at the main effects and interaction of condition by the language group with the random effects. Of course, you should choose random effects based on your design and the model fit and so on. But this is the one I used for this data for now. And for the time course, time window, I took from 800 milliseconds to 0 millisecond relative to the target toward onset. That's because at the beginning, there's not much happening, right? And as I said, for the gross curve analysis, it's best to exclude such like flat window, right? And there's also design-wise a reason to exclude this data because this was the onset of the picture. So this is when the pictures appeared, right? And obviously you can't really move your eyes that quickly in response to the spoken stimuli, right? So it kind of explains why nothing is happening in the early windows. So, and in this study, we are looking at predictive effects. So we're interested in whether participants predicted the target. So we only took the time window before the target was onset. Okay. So that's why we have this time window. Okay. So what we are plotting here is the mean fixation proportion in dots, and the error bar, we can see it around the mean, right? For the target, English competitor, and unrelated condition. I excluded Japanese competitor condition because there was no difference between the Japanese competitor and unrelated conditions. Okay. So if we run this model, sorry, I forgot to say these lines are the model fit. Okay. So if we run this model, what we can find is the overall difference between the target and the unrelated conditions, and or difference between the competitor and unrelated conditions in L1 speakers data. So this is looking at the overall difference. So you can kind of try and draw a line, like flat line for the target condition, unrelated condition, and looking at whether they are different. And there's also the linear term also interacted with the target versus unrelated comparison. So this is showing that the slope was different for the target and unrelated condition, right? So that's pretty clear from the data as well, right? Because the fixation proportion to the target increased much quicker compared to much more quickly compared to the unrelated condition. And you can also see the interaction between quadratic term and the competitor effect. And that also fits nicely with the data, because for the English competitor condition, we see the fixation proportion increased and decreased, right? But that's not the case for unrelated condition. Now let's turn to the L2 speakers data. We see marginal difference between the target and unrelated condition, presumably because the difference was evident only in the later time window. But there's a significant interaction with linear term with the target condition, because we can still see the clear pattern where the proportion increased for the target and stayed relatively flat for the unrelated condition, right? For the quadratic term, this might be a bit puzzling if you compare these effects with this graph. So because for the L1 English speakers data, it's clear because this one, for the English competitor, right, the fixation proportion increased and decreased. And we don't really see such a pattern for the target or English competitor condition here, right? And what I suspect that might be happening is that for the unrelated condition, you actually see this curve like this, right? So for the unrelated condition, it seems that the fixation proportion slightly increased and slightly decreased, right? So this seems to be causing these effects. So there's actually no such tendency towards target and English conditions, but this baseline condition had such a trend. And obviously target and English competitors were compared against this baseline condition. So that seems to be driving the effect. Okay, so let's now check whether the quadratic term I included here was really necessary for this data set. Okay. So to check this, what we can do is to run a model without the quadratic term. Right? So I removed the quadratic term from the previous model, so we now only have poly 1 in the model. Right? Everything else was the same. So if we run this, the model fit looks like this. Right? So what you can probably notice immediately is that, especially for the L1 speakers data, the means, these dots, are often off the model fit line, right? So especially for the English competitor condition, you can see that these dots are really close to the model fit line, right? Not so much for the L2 speakers data, but this seems problematic for L1 speakers data. And I think this is much clearer if you compare it to this model fit, which so this is the model fit for the model which included the quadratic term, right? If you compare, it's really clear, right? In this set, in this model, we can see that these mean dots are much closer to the model fit line compared to this, So we can probably conclude that we want to keep the quadratic term for this data. Right? Maybe you don't have to for the L2 speakers data, but we probably want to for the A1 speakers data. Okay, let's summarize the gross curve analysis. So gross curve analysis is suitable for analyzing a change in fixation proportion, and it's ideal to define the time window for the analysis before the data collection. The second point is really true for any kind of analysis, but it's especially so for the gross curve analysis because it affects the results significantly. It's also ideal to decide which temporal parameters should be included in the model based on a strong linking hypothesis. Right? So do you expect the difference in the slope, or do you expect the difference in peak or in the curvature? Right? And then decide which parameters include in the model based on that hypothesis. Right? And finally, please remember to check the model fit and see if all the polynomials are really necessary for your data. Okay. Okay, so that was, yes.
Brechtje has a question.
Yeah, just a clarification question. So in your data set, so why was the start of the critical window minus 800? Is that where they saw the picture for the first time? So
I set the time window relative to the target word onset, because in this study I was interested in prediction. So what would happen before the target word onset? So I aligned the data all to the target word onset.
But the sentence was presumably longer than.
Yes, sentences were much longer.
Right. So why do you then? How do you decide where to start looking?
Oh yeah, the start of what? Sorry.
Sorry, what?
So start of what?
So how do you decide when to start looking? Because the sentence started already way earlier, right? Than these
yes.
minus 1,000. So why decide where to start looking, let's say?
Right. So sentence started first, and it started with a blank screen. So participants are not looking at anything when the sentence started. And the thing appeared 1 second before the target word onset. So for all items, this is the point, the 1 second before the target word onset. This is when the picture appeared.
Okay.
Right? So that's how, where people are not really looking at anything at the beginning.
Yeah, and it's 800 because you didn't take that part where there's no growth.
Yeah. And then can I just ask a follow-up? So what if you have a different design where you don't have it like this? Is there, because you keep saying, okay, you have to predefine your critical window, but how can you decide that if you don't, like for instance, if you just have the picture already from the beginning, or would you just not do that?
Yeah, you don't have to align your time when there's a picture onset. I just really, it really depends on your design, right? So if you, for example, just have a paradigm where participants see the pictures first and then the sentence is played, and at some point you have a critical word, right? So you can, for example, align your time window to a critical word, and then you can, for example, set your time window to start at the critical word onset. If you're looking at how people process that word, for example.
Yeah. Yeah, I'm just also wondering then how long your time window should be, but I guess that's, yeah,
that's really a it's a critical and tricky question for this analysis, right? I think you can what you ideally want to do is to, of course, take the window where you expect to find the effect, right? And then that's, of course, difficult to estimate if you still don't have the data. Right? If you're just looking at a single word window, like if you're interested in a single word in a sentence or just presenting a word, then you can probably do something like from the word onset to word offset, plus probably some more, some few hundred milliseconds or something. That's one way I feel like. And if you are testing as proficient speakers, let's say if to speakers or children or those groups, you might want to extend that window if you expect a delay in the effect, for example. But yes, that's sometimes difficult to define or decide before you see the data.
Yeah. Okay. Thank you.
I just have a clarification question.
Yeah, another question, Aine.
Yeah.
Can you hear me? Can you hear Chloe?
I'm a little far.
Not clearly, not so clearly. Maybe can you come closer to the microphone?
Yeah, sorry.
Yeah, so it was just a clarification question. So I just wanted to know if each participant saw each of the different 4 options. So for example, they would have heard the cloud like 4 times.
No, they only got one of the conditions.
Okay, so yeah, okay, thanks.
Yeah.
Any other questions from the Zoom room too? No? Alex? When have we determined? Oh, Alex, you can ask questions anytime.
Yeah. I figured that out in the meantime. I was just wondering. I guess I don't know how to pose this question. Well, I was just wondering that, even if the what's it called? Introducing a kind of a higher order orthogonal polynomial term does fit the data better? Like, does that mean it's a real effect of some kind? Like, could it be again just and that's also what I'm always struggling with.
But let me try answering your question. So let's say you have a data like this, right? For the A1 speakers data. Here, you have the look through target, basically keeps increasing, right? And then for the competitor effect, the fixation proportion increase and then decrease quickly, right? And this is often the pattern that you see when we look at the fixation proportion to the target that's mentioned and the competitor that's related to the target, right? And you know that from the previous literature. So we do have a reason to expect increase to the target and then increase and decrease pattern for the competitor, right? So the first pattern, the linear increase, can be modeled using the linear term, right? And the second one, the increase plus decrease pattern, can be modeled using the quadratic term, right? But in this design, for example, we don't really have a reason to expect, for example, participants look at the competitor again. So increase, decrease, increase again, right? If we have such a hypothesis, then it makes sense to include the cubic term, for example, which can model such a pattern, right? But if you don't really have such a hypothesis, it's probably best not to. It was checking with the data, but especially for the cubic pattern, it's very sensitive to the ending of the data. So, for example, let's say I cut the time in here, but there's a very small increase at the end. Let's say it's not there, but let's say if we have such a pattern, it can be captured by the quadratic term, but you probably don't believe that's a big effect if it's a very small increase at the end, right? But the cubic term is very sensitive to such a pattern, right? So if you don't really have a hypothesis to test that, it's probably best not to include that in your data in the first place.
Yeah, I agree.
One more question. Oh, sorry. Alex, you go and then Brett here.
No, I'm going to make it weird. No, I will ask you this later. No, so sorry. No, I was just looking at your stimuli for your experiment.
Yeah.
And I could not help but kind of interpret some of the pictures as their like emoji equivalents. So I'm just wondering whether, that I think that has to be taken into consideration because, if it has like a taboo interpretation, people will look at it and focus on it. Yeah, that's all. Sorry if I made it weird.
Yeah, but that's a very important point. We always need to take account of what the visual stimuli are doing to our eye movement data, because obviously what we want to conclude in the end is how we process language, right? But we have to present something, some kind of visual stimuli in this kind of paradigm. So,
of course.
right. So what I did to exclude possible visual effects. So, for example, some pictures may be somehow attractive to participants for whatever reason, right? So what I did to control for that is to present the same pictures in the failure trials, and the failure sentence was not related to these pictures, right? So if people also look at the certain particular picture in that sentence, when the relevant sentence was played, then we would think that that's probably a visual effect, right? That these pictures are some probably attractive, right? Another thing is that we actually presented these pictures before the eye tracking study, just so that participants will think this is a crown or something else, because this includes a phonological manipulation. It was critical for us that the same word is associated with each picture. So we presented each picture to the participant and told them, okay, this is cloud, this is aubergine, this is pork, and so on. And so they have seen the picture. So they were to some extent familiar with the picture. So it's really not like some pictures was kind of surprising or not
Gotcha.
they were familiar with the picture. So I couldn't express that very clearly, but I probably got the idea.
Yeah, thank you.
Great.
Yeah, Breche?
Yeah, so this type of analysis where you can expect these increase, decrease, then increase, can you also apply that to like a way longer time span? Like for instance, a whole sentence where you expect them to first look at referent 1 and then you're talking about referent 2 and then you expect them to look there and then maybe back to 1? Or is it really something?
Yes, that's possible. Yes, it's possible to apply to a longer window. In this case, my windows were very short. But yeah, if you expect such a pattern for the entire duration of a sentence, it perfectly makes sense to include the entire sentence window to your analysis.
Okay, thanks.
Any other questions?
I set up dualism.
Yeah. Oh, sorry.
Okay.
Oh, sorry. Yeah, Tim, go ahead, and then Janina.
Yes. Can I quickly ask, in the model that you had, I think that this was further down this slide, what is it exactly that you're comparing? Is it just like whether the two curves are similar in a way, or?
So this one?
Yeah, so like the table here, the outputs.
Yes, so the first one, the overall difference is just it's like just an overall LME, just comparing the fixation proportion to the target or English competitor versus the undiluted condition, versus the baseline undiluted condition. And the second one, the linear term, is the interaction between the linear term and the target versus undiluted or English competitor versus undiluted condition. Okay. And the quadratic term is looking at the interaction between the quadratic term and each of these effects.
So,
okay, got it. Thank you.
So Aine, does that mean that for the linear term, you just, if it's significant, it's just basically saying that the slope is different, right?
Exactly.
Yeah. And then the quadratic term is like where the peak is different, right?
Exactly.
Yeah. Okay.
Or one condition may have a peak, like clear peak, like one condition doesn't.
Right. And you're just saying for the L2, there's the same, but that's mainly coming from the peak that's in the unrelated in the quadratic term. Yeah. And that's where the difference is. Yeah. Do you guys get it? Yeah. Okay. They all get it.
No, for L2.
For the L2, Janina, she was saying that it's significant, right? The quadratic term. In the
target, the p-value is kind of set here. It's marginally significant for the competitor, significant for this target.
But those significance is coming because the unrelated has this curve. So there's a difference in this peak between unrelated and target and unrelated English because it's coming from the unrelated peak that we see.
It's just because, like the target, it clearly has like a linear shape and not quadratic. So like, where's even like a peak there?
The peak is coming from the unrelated. Do you see here? There.
Yeah, so it just means that the like target one doesn't have a peak or something.
Yeah, so there's a difference in peak between the target and
so
the
which of
unrelated.
the analysis removes this peak in the unrelated?
Oh, the poly 2. If you exclude that, then you're excluding this peak difference analysis. Is that correct, Aine?
Yeah. Yeah, so for L2 speakers data, it may actually make sense to remove the quadratic term because it's not really showing that effect, not like the A1 speakers data where there's a clear peak for the English composition condition, right? So yeah, it makes sense to remove that from L2 speakers analysis.
Okay, Alex, did you raise your hand again?
Yes, sorry about that. Yeah, I feel like, I've worked with the GCA, but still there's questions. So I'm wondering if there's like two peaks, like one right next to each other. Wouldn't we need like the interaction of poly 1 and poly 2 to be able to say, oh, they're different in time?
Two peaks from two different conditions or two peaks from the same condition?
Two peaks from the same condition.
Right. So like it's a pattern where the diffusion coefficient increase, decrease, increase, and decrease again.
Oh yeah, you're right. No. Sorry. In two
No.
different conditions. If we had two peaks.
Right.
That are
Is that
the same
something
size.
Let me say, quickly go back to where I had some similar. You mean a pattern like this?
Exactly. Yeah, that's what I thought. Is it?
Yeah, this can be captured by the quadratic term because if the peak is different, it might. So in this case, we might find an interaction between the quadratic term and group.
Okay, I see. So the group 1, I guess, would have the higher. Oh my God, coefficient.
It depends on how you code it, but yes, that's wrong.
Yeah, of course. Yes. Got it. Okay, because for some reason I was like, well, don't we like need the linear as well in there somewhere? Okay, thank you.
It can actually appear as a linear too, yes, because if you try and put a linear, it probably will be like this, and for the group 2, it probably will be like, yeah.
Thank you so much.
All right, I think we can move on.
Well, I had a question.
Oh, yeah, Nina.
Yeah, here, like you're saying it's ideal to define. Ideal, you mean the growth curve is ideal, or in principle it's good to define?
In principle, yes, but especially for the growth curve, because of how the results change depending on the time in the choice.
Yeah. Okay. Yeah, that's clear. Thank you.
Okay, shall we move on?
Yeah.
Okay, then. Yeah, I noticed I'm very much running over time, but let's continue. So now let's look at the cluster-based permutation analysis of CPA. So this analysis was originally developed for the EEG or MEG analysis. So you might be familiar with the literature on EEG or MEG, but this has been applied to the visual world paradigm data too. So that's what we are going to look at today. So the advantage of CPA is that it maintains a statistical power, that's what we want, right? By controlling for the chance of false positive. So without increasing the rate of false positive too much, we can still keep the power to a good extent. And the data also don't need to meet the assumption of the parametric test because this is a non-parametric test. So unlike ANOVA, which has a parametric test assumptions, we don't have to care about that in the CPA. So how that works, so this is the example from the EEG data. So the graph is a bit small, but we look at the analysis flow, how we apply this analysis. So what we first do is to detect the clusters with a significant effect. So what we do first is to, let's say this is data, right? And then we want to compare these two lines. So these two belong to two different conditions, right? Again, this is from EEG data, so that doesn't look like an eye tracking data. But let's say we run multiple t-tests and then test in which windows these conditions differ, right? And then we can then have something like this that's plotted here. So if, for example, this bit shows a significant effect, then that's plotted as a cluster here, right? So the first step is to run multiple t-tests and then where we find the significant effect, right? And then these are the clusters or consecutive time windows that show the same effect. So same effect, I mean significant effect, the same direction. Okay. So we can then have multiple clusters like this. And then the second step is to compute the cluster mass statistics for each cluster. Okay, so in this case, we have these clusters. The cluster mass statistics for t-test is just the sum of t values, right? So if you do t-test, you can get a t value, right? You just add up all the t values you have for each cluster, right? So that's what we do in the second step. In the third step, we permute the data for each predictor and obtain another distribution. So that means we shuffle the data. So for example, if we have condition A and B, we just change it sometimes keep it the same. Right? So we shuffle the data. And then if we do that many, many times, we get the null distribution, right? Because we just randomly assigned the condition, right? That's what we do in the third step. In the fourth step, then we detect the clusters in the null distribution, right? So we get the null distribution data from step 3, and then we can again do multiple t-tests and see which clusters we get in that distribution. And then similarly get mass statistics, cluster mass statistics like we did in step 2. Okay. And finally, we can compare the mass statistics that we got in step 4 and those we got in step 2. Right. This is probably a bit vague at this point, but we have the tutorial where we look at the code, so hopefully these steps will become clearer when we look at the tutorial course. So that's the analysis flow. And the advantage of C-LaBL. So the disadvantage is that they can't really tell the exact onset or exact offset of an effect based on the cluster. Right? And there's a really good paper actually on this topic. So if you're interested in more, you can read this up. But to basically make the point, this is just what we looked at, right? So if we have the multiple clusters here, and let's say if we run the cluster-based conditional analysis, we find that only this cluster was significant and everything else we reject, right? And let's say when we have this, we can't say that the effect started here and ended here or lasted for this long, right? And that's because this cluster is directly taken from this cluster, right? And this is based on the uncorrected t-value. So this involves multiple comparisons. T-values are not corrected, right? And so we are not really testing that, or we actually got here is not that in every bin that's included here, the effect is significant. That's not the conclusion that we can make, but rather these conditions differed, right? And at some point in this cluster, but we can't say from when to when based on the cluster-based permutation analysis, right? So we just should be a bit careful about the interpretation, like how to interpret the cluster. Right? We can conclude that these conditions differ in the window that we looked at, but we shouldn't conclude that this effect started at this point and ended at this point or lasted for blah blah millisecond. Okay, so let's apply this analysis to the same data set that we just looked at. So again, this was the data. Right, let's see if what the result would look like when we apply the C-LaBL to this data. And for comparison, we have the multiple comparison results plotted at the top. So we can see, sorry, it's a bit small, but we can see multiple white circles at the top and black circles on the second row. Right, this is showing the results on the linear mixed effects model. So if we run the same LME in each 15 millisecond time windows, so that's multiple, that involves multiple comparisons, right? So that's what we shouldn't do. But if we do that, what we get is the significant effect from around here to here for the target versus unrelated comparison. And for the English competitor versus unrelated comparison, we get these 3 time bins that are found to be significant. And similarly for the L2 speakers data, we see something happening at the beginning that's showing the significant difference between the target and unrelated condition. But we probably want to think about, okay, these are 2 bins, 2 consecutive but still 2 bins. Is this really significant? We probably want to run this test. Right? And there are more bins that turn out to be significant in the data time window, and also we have a similar consecutive bins that show the significant effect for the English versus unrelated condition here. Right. So let's see how the results look like if we run the CPA here, especially for the target versus unrelated condition, and also here what would happen to these bins for the A2 speakers data. Okay, so I plotted these bars at the bottom, and this corresponds to the cluster, significant cluster. Okay, and you see one line is a bit thick and one is a bit light, and that's because I run by subject analysis and by item analysis, and so if both analysis show the significant effect, this line is a bit in a darker shade. And if it was found only in the item or by subject analysis, it's a bit lighter here. Okay. So what we see here is the significant cluster for the target versus unrelated comparison, right? Roughly corresponding to these windows, but the LME studies show significant effects very slightly earlier compared to this. And for the English compressed effect, it actually seems to correspond to these bins that were detected in the LME analysis. But for the L2 speakers data, now we can see that the cluster was detected here, but this one that corresponds to these 2 points at the beginning was not detected. So we can then conclude that this was probably by chance. Right? And we can similarly see that towards the end of the time window, we also see the cluster for the English compressed versus unrelated condition comparison. Okay, so this is application of CPA to the data. Just to summarize, so the CPA controls the chance of false positive while maintaining a statistical power. And it can't test a change over time like the growth curve analysis. It doesn't really test a linear or peak of these effects. It can only detect the difference between the two conditions. But the data don't need to meet the assumption of parametric test because it is a non-parametric test. And last thing to note is that the results don't reveal when the effect started or ended. And so that's something to keep in mind when you interpret the results. So that's the CPA. Any questions for this part?
Yes.
Yes. If you go to your first example of the data, so you have like not your data, but the one that you showed before this.
This?
Yeah. So here you have yeah. So there's different. So it's like the t statistic is positive in the first cluster, but negative in the later clusters, right? So, but then you're saying that you have to add them all up. So then don't they like cancel each other out? Like, can you?
No. Sorry. So in each cluster, the effect should be in the same direction. So in this cluster, for example, it should correspond to the positive effect, and this cluster should correspond to the negative effect. But there should be no effect going into two different directions in the same cluster. If there is such one, they should be in a different cluster.
Yeah. So per cluster, you compare it to the sort of the baseline and. So you do the analysis, let's say per cluster, not for all of them together.
Yeah. So each cluster is compared against null distribution separately.
Okay, then I misunderstood. Okay, thanks.
Any other questions from the Zoom? Okay, I think we can go, Aine, since in the first one there were lots of questions. So.
Okay, let's now move on to the bootstrapped difference of time series or B dots. So again, here the differences again, you can find them in the paper. Okay, so I just repeat. So the advantage of B dots is that we can test when an effect starts or ends or how long it lasts, which we couldn't test using CPA, right? And it also controls the family-wide type 1 error that can arise from autocorrelation, right? And it uses a modified Bonferroni correction to do that. So if we run what is a modified Bonferroni correction? Right? So let's say again that I brought up the same data from the previous example. So let's say we run 10 tests for this window. Right? So I take each 100 millisecond bin as one bin, and then run the t-test or whatever in each bin, right? And if we do a standard Bonferroni correction, what we do is to divide the p-value by 10. That's the number of tests we run, right? So in this case, we run 10 tests, so we divide the p-value by 10, and we use that p-value as a threshold, right? But if we do this, we don't really consider the autocorrelation, right? Because we are saying that each test is independent, right? Or this kind of Bonferroni correction assumes that each test is independent. But that's not really the case, because as you see, the data here is similar to the data here compared to the data here, right? So the data in adjacent bins are similar to each other, right, compared to the non-adjacent bins. Right, so if we just apply the standard Bonferroni correction, we're making it overly conservative, right? So that we lose the statistical power, right? So in the modified Bonferroni correction, what you do is to estimate autocorrelation between test statistics, right? So if we do a t-test, for example, in this bin, it should be to some extent similar to the t-test result in the adjacent bin, right? Because of the autocorrelation, right? And then so use that use that data to estimate adjusted alpha. And this is less conservative, but maintains an overall family-wise error to the specified alpha. That's how it accounts for the family-wise type 1 error rate. An advantage of Beaded is that it can use two types of curve-fitting functions. One is called 4-parameter logistic, and the other is called double Gaussian. Okay. And this is it kind of includes also math, but you don't really need to look at these things. The important thing is that the 4-parameter logistics is used to model fixation proportion that just increases, right? And double Gaussian is used to model fixation proportion that goes up and down, so increases and decreases, right? And we already know these patterns for the visual world data, right? The first one can be used to model looks to the target, right? When you say a word, and then when that word is depicted in as a picture, then people start looking at that target, right? The second one can be used to model a compressor effect, right? So if you hear a beaker and then there's a beetle, then you might temporarily look at the beetle, right? But eventually you decide not to look at it anymore, right? So such a compressor effect can be modeled using the double Gaussian function. And this also nicely fits with the data we already looked at, right? So again, you've already looked at this many times, right? You can use the 4-parameter logistic to model this pattern, right? And then the double Gaussian function to model this pattern, right? So nicely usually matches the pattern with pattern looks to the target and the pattern looks to the compressor. Okay, so for the analysis flow for this analysis looks like this. So you first estimate fitted curves for each subject. Okay, so you have data for each subject and try fitting curves for each subject separately. And then you inspect the fitted curves and compare them with the actual data. And then check the values or how similar the fitted curves are to the actual data. And in the third step, you draw random samples for each subject curve. So you bootstrap the data, randomize or shuffle the data, and then estimate the standard error of the mean in each bin for the sampled subject. Okay. And then next, you create a population mean, so that's the mean for the group, right? By averaging all the sampled curves. And finally, you use estimated mean difference, the standard error, compute t-statistics, and then estimate an adjusted alpha. Okay. And what's really important for this analysis is to check whether the curves are good fit for your data. So good example looks like this. So in this case, we are fitting the double Gaussian curve where the fixation proportions goes up and down, right? And we are looking at the fitted curves in the blue line here and the actual data, the observed data in this dotted orangish line. And we can see these are roughly close to each other and deviate too much from each other. So this is a good example of curve fitting. Not so good example looks like this. So this is trying to fit the 4-parameter logistic to this observed data, right? And then this is not really doing a great job, right? So we can see, for example, at this point, the observed data is not very close to the fitted curve, right? There's even worse data, again, fitting a 4-parameter logistic. So in this case, at any point, only these 2 points are the observed data close to the fitted curves, but it's really a terrible fit. Right? So you shouldn't really proceed with if your fit looks like this. Okay, so I talked briefly about the disadvantage of readouts, and so as we've seen before, the specified function may not really capture some participants' curves, or although it might capture others very well. So let's, for example, see in this case, we did fit the 4-parameter logistic curve. So that's suitable for fitting the looks to the target. That only increases, right? But the observed data actually increases and decreases, right? So in this case, it actually may make sense to use double Gaussian fitting function instead, right? So sometimes that can happen. So what you want to do is to try refitting, perhaps using a different curve fitting function. Like if you think the different function might be a better fit for your data. And available curve fitting function seems suitable for analyzing a single word window, right? So these might be suitable for looks to the target or competitor word, right? But you sometimes want to look at something else or a longer time window, right? Where the fixation proportion doesn't have such a clear pattern with either just increases or increases and decreases, right? You may have some different pattern, right? In that case, you might not be able to use these available curves, curve fitting functions for your data. And a VDOT can't also capture cross-random effects and can't compare time course estimates between conditions or groups. Right? So if you are interested in the time course estimates rather than the overall difference, then it might be better to use another approach. Now, I wanted to show you the example of using this analysis to my data, but I couldn't fit the curves to my data at all. So if I just look overall data, I just picked up some of the participants' data here. This one is not like too bad, but this one is terrible, right? And this one probably neither curve fitting function can fit a good curve to this data, right? So I found 4 fits overall, and this is very problematic because this would make the standard deviation estimates extremely large. And so we shouldn't proceed if we can fit the curves to our data. So why this might be happening is that the curves for the observed data, like that's the orange dotted line, they're not so smooth, right? And so this is kind of here, you see lots of change over time with multiple peaks, right? And in this study, we did not have many items. So if we divide the data for each subject, you don't have that many data points for each subject, right? So we couldn't really draw a smooth curve for each participant. So that's probably why the data is not so smooth, and that's why the curve fitting didn't work very well. Right. And I just looked at other successful application of VDOTs, and they had much larger number of trials, like 200 or 300. And I only had 16 items. So that's the difference we are talking about. So if you want to apply VDOT, you want to have enough number of items so that you can end up with a smooth curve for each participant. Right. And it's always important to inspect the curves before you do the analysis. So you shouldn't proceed if you curve fitting looks like this. Okay, so to summarize, so VDOT can fit a 4-parameter logistic or double Gaussian curve to analyze links to the target or competitor object. And these curves are suitable for visual paradigm time course data, but not always. It's mostly useful for single word processing experiments. And it can test when the effect was significant, so when the effect started or when the effect ended or how long it lasted. And it controls the family-wise type 1 error rate using a modified Bonferroni correction. Okay, any question about this bit?
Questions? No.
No? Okay, let's proceed then. Okay, then we can move on to the generalized additive modeling or GAM. And here again, the references for GAM. Again, these were referenced in the paper. So you can look at them from there. This is right. The advantage of GAM includes that it can test when an effect starts or ends, or how long it lasts. So it's similar to BOTS in that sense. And it can model non-linear as well as linear time course data. So if your data have like a non-straightforward pattern, like not linear, not quadratic or something that looks a bit different, GAM may be a good choice for you. And it also controls the autocorrelation, and it does so by including an autocorrelation parameter in the model. So autocorrelation is modeled in GAM. And it can model complex curves using what is called thin plate regression spines. So, for example, this one was like the linear polynomial what we looked at in the gross curve analysis, right? And this one is like a quadratic one, and this looks like a cubic one, right? But the GAM has much more functions to model the time course difference. So it's good at modeling relatively complex change, complex time course effects. Also, it comes with disadvantages. So it can't statistically compare the onset to offset of the duration of effects. So it can detect the onset to offset, but it can't compare these offset to onset, onset to offset across different conditions. So if you're interested in time course of estimates, so for you want to know whether onset for one condition starts earlier than the onset for the other condition, and then use another approach. And if your data are binomially coded, for example, I code 1 for if the object is fixated and 0 if the object is not fixated, right? If you have such binomially coded data, you can't account for the autocorrelated errors. So the model can't take the autocorrelated errors into account. The solution for that is to convert the dependent variable to a non-binomial format. So you might, for example, consider using empirical logic transformation to treat it as a continuous variable, for example. And the model parameters, like coefficients, are not really easy to interpret, as we'll see in the next slide. But it's not really a problem because we use a difference plot to estimate the onset to offset thermal effect. Okay, let's now look at the analysis flow for So what we first do is to fit what we call a base model to determine the appropriate value for the autocorrelation parameter. Right? So we want to include autocorrelation parameter in the model. So we first need to estimate what to include in the model. Right? So what we're running here is the model testing an effective condition. In this case, we're just taking L1 speaker's data. So we are testing the difference between the red line and the gray line here. Right, and right, so if we run this, we can test that. And the random smooth is something like a random effect that we include for LME linear mixed effects models right? Well, here we have what is called random smooth, and that incorporates both random intercept and random slope effect. Okay. So we are going to look at this in a bit more detail during the tutorial, how to define random smooth. Okay. So you run this base model first, and then you can obtain the autocorrelation parameter based on the model. And then we can run the main model with the autocorrelation parameter in. Right? So in this model, everything up to this point is the same. But we here have the value for the autocorrelation parameter, and that is included in the model using this bit code. And then this is just specifying the first bin in the data. So if we do this, this is the autocorrelation, so the data with autocorrelation in, and this is showing the correlation between the adjacent time points. Right? So this is on the x-axis, we are looking at the time lag. So if the time lag is 1, we are comparing to adjacent time windows, and then if the lag is 2, then we are comparing the time being, let's say, the first and third time being. One time is in between, right? And so autocorrelation parameter is, of course, 100 for the time lag 0 because we are comparing the same data with the same data, right? And we still see a high correlation if the bin is adjacent, right? So there's almost 0.8 correlation, right? And then it still kind of decreases, of course, when the lag is large, but we still see huge correlation here. But when it's taken into account using this version of the model, we see that autocorrelation is significantly decreased. So the model has taken the autocorrelation into account. Okay, so when we get the summary of this model, what we get is something like this. Right? And so this is different from what we often see in the model summary for LME, for example. Right? We have a bunch of time and time subject and time item seemingly interacting with the target condition or unrelated condition. But what do these actually mean? Right? So these are kind of hard to interpret. What does it mean when the time interacts with the target condition or time interact with the unrelated condition, right? So to get what we usually want when we run GAM, we plot the difference between the target and unrelated condition across time. So what we're plotting here is the time, and then empirical is a transformed fixation proportion for the target and the unrelated condition. And this is a difference plot. So if you plot something like this, this will tell us when the effect started. So that's the red dotted line here. And when the effect ended, that's the red dotted line here. And this is how long the effect lasted. Right? So when we run GAM and want to test difference between the two conditions, we typically look at this and not this. Right? So that's how GAM works. Okay, to summarize, so GAM can model nonlinear time course data, and it's especially helpful if the time course data look a bit complex. And it can test when the effect was significant, so when it started to occur and when it ended. And it controls for autocorrelation by including an autocorrelation parameter in the model. And we can plot difference curves to estimate the onset and offset of the effect. You usually don't really look at the model summary to conclude when the effect started to ended. Okay, any question about this bit?
Any questions from Zoom as well? No? Okay. Yeah, I think we're good, Aine.
Okay, I have 10 bit more slides. Maybe I'll finish off then.
Yeah, and then maybe we could take a quick break and then go for the tutorials. Yeah.
Okay. Okay, then I finish the talk with divergence point analysis and finally talk about which analysis you should choose. And here's the reference again. So Kate Stone shares their script on their OSF page as well. So if you want to look at the original script, you can go to her OSF page. So the advantage of the divergence point analysis for TPA is that it can estimate the onset of an effect and the confidence interval. Okay, so you can actually compare the effect across different conditions. And it controls for the autocorrelation in the time course analysis. So let's look at analysis flow. So what you first do is to run an uncorrected statistical test at each time point. So you run a bunch of, for example, t-tests at different time points. Right? And then you take the first time point in a number of batteries, let's say 10 or 20, you can decide, or you will decide which number you will put in this X. Right? So let's say 10 consecutive time points with significant t values. Right? So if I choose 10, for example, I run t-test many times here. And then if I find, for example, started finding difference between these two lines here, and then it kept showing significant effects for the 10 consecutive time bins, then I take that first point of the bin and then keep that for the second step. So you do that for the second step, and then you boost up the data by participants, time point, and object many times. Right? So this is similar to what we do for CPA, but in this case, you do that. You don't shuffle different conditions. Your aim is not to get distribution here, so you only shuffle by participant, time point, and object. So you do that many times, and then this will generate the distribution of divergence point, right? So when you do it once, you get one divergence point, right? And if you shuffle the data, and then you compute the first consecutive time points where the effects started to be significant, then you get lots of divergence points, right, for the shuffled data. And then you can take the mean of these lots of divergence points, and then you can also compute the confidence interval based on the variability. Okay, so you might get something like this. So this is now a histogram for the divergence point. So you can, for example, if the divergence point is here, this will contribute to the data here. And then here the divergence point is here, then it contributes the data here, right? Just like a histogram. And this is showing the first time points that are sticked in the original data. This is step 2 here. So this was, if we run lots of t-tests and then detect a divergence point, we find it here. But if we run it many times on the shuffled data, we can find the mean around here, and then in confidence interval from here to here. Right. So that's what you can get from this analysis. But there are also disadvantages. So the PA can't estimate the duration of effect or multiple divergence points. So it can only estimate one divergence point, the first one, and it can not test how long the effect lasted. So for example, if you have data like that, and 2 divergence points, let's say this one is divergence point for this difference, and then the second one is for this difference. You can only test one. So if this is not significant, this will appear. If you detected this one, then this won't appear in your analysis, in your results. Okay. Also, probably more important one is that it's not suited to test whether an effect is present, whether an effect is significant. Because this analysis assumes that you already have an effect, that is, these two conditions are already different. Right? Because the aim of this analysis is to test when the effect started to differ. And so it's not aimed at testing whether the effect is significant. Right? So it can't really compare the two conditions. So what you usually do is to use another analysis to test that condition A is different from condition B, and then use the divergence point analysis to test when the effect started to occur. Okay, to summarize, so you can estimate.
Sorry.
Yeah. Sorry, could you?
Yeah, Judith has a question. Sorry, we need to come up to the.
Sorry.
No problem.
What exactly do you mean by an effect? So if you mean, for example, I would say an effect of prediction, and I find that the onset of divergency between the target picture and the competitor picture is prior to the onset of the critical word, then I could say there is an effect of prediction, right?
Yeah, what I mean is that you can't test the difference between the two conditions or two groups.
Okay, so so because if you were interested in something like prediction, then I mean the onset of divergency gives you what you're interested in.
Yes. Yeah. Yes. Yeah. So if you're interested in time points, when when the difference starts to occur, then you can conclude based on that. But if you're interested in, let's say, maybe let me put it this way. So if you're interested in the difference on the x-axis, right? So in this way, when the effect starts to occur, then you can use divergence point analysis to test an effect. But if you are interested in the y-axis difference, right? So when the condition attracted more fixation than the other, divergence point can be used to test that.
Yeah. Okay. Yeah. I get that, because it depends on what effect basically we're interested in. Okay.
Yeah. Sorry, I was a bit unclear on that. Yeah. Thank you.
Any others? Okay. Yeah.
Right. So yeah, that was the. Did I say the summary? I think I haven't. So yeah, the PA can estimate the onset of an effect, and then the confidence interval. So you can compare the onset between different conditions or groups, and it can also test whether the onset. So that's what I already said. The onset differs as a function of condition or group. It can also compute Bayes factors that wasn't included in the paper because this is actually relatively new, and so I wasn't aware when I was writing at the paper. But it can be used to compute Bayes factors. So the first point is assumes that the effect is present. So that's reiterating the point that I just said. It can't be used to test whether the effect is significant. It can't test the difference, fixation proportion difference between the two conditions or groups. Okay, let's now look at the application of this analysis to the same data that we already know. You know the design, you know the data. So let's see. So these points again were significant data points detected if we run lots of LME across multiple time windows, and the same for L2 speakers data, right? And if we run the divergence point analysis on these data sets, we get something like this. So this is showing the mean divergence point for L1 speakers and the confidence interval. Right? And the same for L2 speakers. The confidence interval is much larger, presumably because the L2 speakers data had more variability compared to L1 speakers data. And if we plot the histogram, we can, see that more clearly that the L2 speakers data are more widely distributed and compared to the L1 speakers data. Right. And we can also notice that the confidence intervals don't overlap. Right. So we can, based on that, we can conclude that the onset was significantly earlier in the A1 group compared to the L2 group. Okay. Let's then summarize the overall the analysis and which method you should be using for different purpose. So first of all, first question you probably ask is whether you are interested in the time course of an effect. Right? So if you are interested in when an effect occurs or how long it lasts or those questions, then your answer is yes. So you'd either go for one of these analyses that I just explained in this talk. If you are not interested in time course effect, you can just go for the usual suspects like TSS standard boundary me. Right? Now, so let's say you say yes. Here, you have several options to look at. So if you wanted to control for autocorrelation, almost all analysis does except for the growth curve analysis. If you wanted to compare the fixation curve, like so difference in slope or peak, then you might want to go for the growth curve analysis. None of the other analysis can statistically compare different curves. If you wanted to estimate the onset of an effect, so if you want to know when an effect started to occur, you'd want to go for B dots or GAM or DPA. And if you want to statistically compare the onset of an effect, so if you want to know whether the onset was earlier in one condition than in another condition, you'd want to use DPA. But DPA doesn't detect an effect. So you'd want to use another analysis to first detect an effect and then use DPA to test when that effect starts to occur. Right. So there's a summary table for different analysis, but you can find the same table in the paper and it kind of say the same point as the previous one. So I think I skipped this one. But feel free to ask questions if you have any about this table. And it's also fine to combine different methods as long as you're testing different questions using different analysis. Right. So for example, you can run the cluster-based permutation analysis to detect an effect first, and then use the divergence analysis to estimate when that effect started to occur. Right. And these are nice a nice combination of analysis because the CPA can't estimate the onset, like as we've seen, and the EPA can't detect an effect, right? So they complement each other nicely. But one thing that I get to note is that don't use one analysis to select a time window and then run the second analysis, testing the same question in the selected window. Right, because what you are doing is to find the optimal window to find the effect you want to find. And then that's what you're doing in the first bit. And then you are using that optimized window for your second analysis, right? And so, for example, for example, might be to use GAM to detect when an effect occurred, and then use the time window that was detected by GAM and run an LAB on that on that window. Right. And this is called double dipping or circular analysis. Again, testing the same question using testing the same question using two different methods, and use the first analysis to select the time window for your analysis. Right. That was all. If you have any questions, I don't know, but you can also email me if you have any questions after the workshop too.
Thank you, Aine. So, Aine, should we take a break and then we can start on the tutorials?
That's good.
Yeah, just one more question from Brechtje.
Okay. I was just wondering if you're interested in like individual differences, or let's say, the effect of exposure or something, or proficiency. Is that in any way compatible with any analysis?
Yes. Let me see. So gross curve analysis, you can include individual difference. So you can just do that, just like you do for LME. Like so, at let's say like proficiency in the continuous measure to the model, and you can just like you do in LME test an interaction between that and other variables. Other things, so DPA, so these analyses that test difference between the two conditions, it is really aimed at testing the difference between the two. So you can only look at individual differences, like for example, by dividing the participants into two different groups. So it's not really straightforward to look at effects of continuous independent variable.
Okay. Thank you.
All right, so then we are pressing for time, right, Aine? How long do you think the next tutorial part? Should we just say we'll come back in 10 minutes, so 11 for Norwegian time? Is that okay? Okay.
That's good to me.
All right, okay, so see you guys back at 11 Norwegian time. All right. アイネちゃん、あと何時間ぐらいかかりそう？あと1時間半ぐらい。
ちょっとごめんな、めっちゃ押しとって。
すごい質問あったから多分良かったと思うんだけど。あと、今日2つやる？
そうやな、うちは別に後ろ何も詰まってないから、つってみても大丈夫やし、ワークショップ的にはそれ大丈夫なんかな。
じゃあ最初の growth curve と、あともう一つ？OK。
でちょっと、どんだけかかるか見てみるか。使うデータ自体は一緒やから、今見たやつやから、 データ見る部分とかは結構、サクサクっと進めてもいいかな。
OK。そしたら、まあちょっと押しても大丈夫なんだけど、12時15分からもう一個ミーティングがあるから、
そっかそっか。じゃあ、
それまで
でもそれは多分大丈夫。大丈夫。今11時だっけ？
今11時だから1時間15
もうすぐ11
分。
時。だって、クローズカーブ終わって、なんか30分以上使っとったらちょっと、
やばいな。
明日に見越しただけ。
そうだね。今日じゃあ、グロースカーブと、あと何
クラスターパーミュテーションやろうかなと思ってたけど。
クラスター、クラスター。じゃあその2つを目安で、それ、まあ、グロースカーブがエクステンドしたら、そこで、
明日4つやるみたいな。明日4つやっても大丈夫。
OK。じゃあちょっと時間見て、だってクラスターやって、途中で終わるのもあるじゃん。
そう、途中はちょっと一番あるよな。
そうだよね。OK、了解。じゃあ、ちょっと様子見ます。じゃあ、アイネちゃんブレイク取ってごめんね。
はい、ではでは。
はい、ありがとう。じゃあね。あと5分後。はい。All right. Okay, so now it's gonna be more tutorials. So yeah, if you have any questions, just for the people in this audience, let me know, and then maybe if you get stuck, you can do a share screen. But we only have 1 hour left, so it'll be a little bit more quick today, but there'll be more sessions tomorrow too. So yeah, okay. So Aine, please, the floor is yours.
Okay. I'd like you to launch a tutorial for the growth curve analysis. So those who have downloaded the tutorial already, please run. Let me type that in the chat. Run those in ROR Studio to launch the tutorial for the growth curve analysis. I'm sharing the one that I launched. So if you didn't have success downloading the tutorial or the package, you can just watch me do it and follow along. So share.
Yeah. Sorry, one quick thing. I think there were some people who couldn't download the tutorials. If that's the case, then I can be on Zoom after this and we can go through it together. Especially I think there were some in the Zoom room that couldn't do it. So for now, you can just follow Aine's, what she's explaining here. And yeah, we'll set it up for you for tomorrow if you haven't downloaded it yet. So, okay.
Thank you. Right. So, yeah, the setup looks like this. So these are just saying the packages that you need to install to run the tutorial and the analysis. So that's what you have done already if you are able to launch this tutorial. And the package that we are using to run the growth curve analysis is from Dan Mama's website. It's called GazeR. And we are using this package to compute the polynomials that we need for the growth curve analysis. Okay. And this one is just an optional. So if you run this command, you will get numbers in the like what I call normal number format instead of these kind of format that are used by default. So if you don't need that, then skip the command below. So that's just a setup. Let's go to the next topic. So the data we'll be using is from the data set that we just looked at during the talk. So the data we're looking at here is the fixation proportion data coded binomially for each 15 millisecond pin. Okay. So the time is from 1 second before the target word onset and after 1 second after the target word onset. And count is the variable that's coding the fixation proportion. So 0 is not fixated, 1 is fixated. Okay. And we have 4 conditions. I just abbreviated it to tag, ing, Jap, and for the target and English competition, Japanese competition, and related conditions. Okay. If you open the tutorial, you can check the description for each value here. But what's important is just the subject, the time, count, value, and the condition, item, and the language group. Okay. And when you use this data, so this data set comes together with the package that you downloaded. So if you wanted to use it for your practice or something, you can always do so. And you can use this help page here to look at the data and the description of the data. Okay, so we use the data from 800 milliseconds before the target word onset to the target word onset, as I just did in the during the talk. Right, so, and we also dropped the Japanese condition because we didn't find any difference between that condition and the unrelated condition. So this is just that what it's doing. So we're creating a new data called fixed binom grid. And we're taking the original data set here and filtering it based on the time. So from -800 to 0. And we are only taking the target, English competitor, and unrelated conditions, and then dropping the level that we don't want. So we are dropping the Japanese competitor level from the condition factor. Right, and in R, you would usually want to use an informative name for the data set. So I just called this grid because it's the prediction time window that's before the target word onset. Okay. So now we need to create a second order polynomial that's basically linear and quadratic terms. Right? If I say a third order, that means linear, quadratic, and cubic. Right? We create that using the variable time and within the selected time. So to do that, we use the function called poly from the GazeR package. So the code we want to run is here. So we're taking the same data set here and then running the function called poly, right? And then again, this is the same data set that we created in the previous step. And we put the predictor, we put time in the predictor because we use time to create the polynomials. And the poly order, if we set it to 2, that indicates that we want linear and quadratic terms. Right? So here, that's what I written here. And if I put orthogonal equals true, then as says I want orthogonal polynomials. Right? If you put false, you get natural polynomials that where the poly 1 and poly 2 are correlated to some extent. Okay. And if I set draw poly to true, then we can get this plot. And this is a good to plot so that you can just double check the time window that you took and how the polynomial looks like. That is not looking like a natural polynomial, for example. Okay. Okay, so if we run this and get the data set again, we see, so this is plotting the summary of the same data set with the poly 1 and poly 2 added in the data set. Right. So if we run this command, these two columns will automatically be created. So poly 1 corresponds to the linear term and poly 2 corresponds to the quadratic term. Right. So we can use these values now to model or and the cross curve analysis. Okay, now it's called the categorical variables. So if you are familiar with LME, this is what you do for the LME too. Right. Here I'm using dummy coding for the condition because we have the baseline condition, unrelated condition. So we are taking that as a reference level and using some coding for the language group. Okay. So that's what I'm doing here. So this is checking a default condition for the condition, right? So by default, the first level is called as the reference level. So first level in this case is a target, so it's called as the reference level. We will change that later. And this is also called using dummy coding, and the first level is called as the reference level. So we will change that so that the unrelated condition is now the reference level for the condition. And for the language group, we use some coding. So we just use control sum function to do some coding for the language group. And we can check the data once again. It does nothing to the data. It's just that it coded the condition and the language group differently. So that's the preparation for the data and looking at the data, right? Okay, let's go to the next topic. Okay, now we can fit the model now that we have the poly 1 and poly 2 values added to the data and we have coded to the categorical variables. Now, in this tutorial, we just fit the simple random effect structure model just to save time. So if you run a complicated model, it takes more time to run. So that's why I just remove the complex random effects. But obviously, when you apply this to your own data, please choose the the random effects according to what you want. Right. So this is the generalized media mix effects model testing an interaction of condition by language. So here we have the condition by language, right? And the effects of each effect. So effects of condition and effects of language group. And also includes the interaction of poly 1 by condition and poly 1 by language, right? And poly 2 by condition and poly 2 by language. Right. And then the three-way interaction of poly 1 condition and language and poly 2 condition and language. Right. That's what we have in the model. Right, I said that already. So when you run this model, please choose the best random structure for your design data. So we can just run this. Right? So this is specifying the generalized mixed effects model. The dependent variable is the count in your dataset. And then this is what we want to test, plus the random effects here. And then I call it the family to binomial because our data is binomial, so either 1 or 0. Right. And then this is the data we're using. Okay. Okay, so we can fit this and then go to the next topic. Okay, so we can now plot the model fit now that we have the model, right? So we can do so by using a fitted function. So this is the model that we got from the previous function, right? So we just put that in the fitted function. And then we can add this to data that we had. And then we're creating a new column called model fit. And so the model fit values are added to this data set. And I don't think I'm going to the detail of ggplot. I think you know how to plot these things. And so if I just plot the model fit, right? So this is plotting the means using these dots and then the model fit using these lines. So this is what you saw during the talk, right? So the same data, same thing, right? So this is when you can check the model fit, right? If the model fit is good, then these mean these dots are representing should be close to the model fit line. Right? So that's what you want to check when you plot this data. Now we can check the summary of the model. I just use a summary function as you usually do for an LME. And we have this long fixed effect. Right? So we can find some stars running up here. So we can check which one is significant here. Right? So we look at the conditions first. Right, so you can see that the condition 1 and condition 2 are both significant. Right, so okay, we can do a quick quiz here. So what do these suggest? You can do a quick quiz here. You open the tutorial here, and then yeah, tick the correct answer there, and then you can submit the answer using this one here. Maybe I give you 1 minute, or let me know when you're done. It about good times. Does anybody need more time?
So that has to be downloaded from our tutorial.
No, I couldn't find it, but I see it.
Yeah, okay.
If you haven't downloaded it, you can check it here. see which one you think is correct. Perhaps note it down somewhere so we can check. We good to proceed? Are we good to go?
This English imperative was, for instance, 1, and the others were both 0. So isn't it then compared to both other conditions?
sure what you mean.
Doesn't this mean that it's like English is compared to both that and that? If the others are
no, so the unrelated is the reference.
Yeah, but how do you know that? Because if they're both coded as 0, then
what do you mean?
If something is coded as 0 and the other is coded as 1, then the comparison is between 1 and both zeros. But maybe I'm wrong.
Yeah, but then it takes into account this and this. So this is 1 here, but this is 1 here. So then overall, this will be the reference level against this one and then this one.
Okay.
So yeah.
Shall we go or shall we wait a bit more?
I think people are submitting their answers, but I'm not sure.
Okay, I mean, I don't see the submitted answers.
She doesn't see it.
I mean, so I can't see the submitted answer. It's not like I don't know.
See it. Oh, okay.
I can see. It's not submitted to me.
Oh, okay.
So please let me know if you're done.
Yeah, okay. I think some people just have trouble opening the tutorial, but I think
right.
Yeah, it should be. Should we write in the chat, Aine, or?
It's fine.
So people in the Zoom room, just tell us which.
Yes, I now saw the chat. Sorry.
Yeah. Answer 2. Tim. Answer 2. Yeah. I choose.
Shall we stick answers?
Yeah, I think we're good. I know. I think 2 was the most.
Yeah.
Was the popular one? Okay. All right. So let's look at one. So the first one is looking at the difference between the target and the English competitor, and the difference between the English competitor and the unrelated object. Right. So that's the option 1. The second one is looking at the difference between the target and the unrelated and the English competitor and unrelated condition. Right. The last one is comparing the difference between the target and unrelated versus the difference between the English competitor and the unrelated condition. Right. And just to remind you, how we coded the condition was like this. Right. So the unrelated condition was the reference label equal to 0 here. Right. So the target condition was compared to the unrelated condition, and the English competitor was compared to the unrelated condition. Right. And each comparison corresponds to the first one and the second one. Right. And what we have here is the condition 1 and condition 2. So the condition 1 corresponds to this. So comparing target versus unrelated condition, and the second one is comparing the English competitor versus unrelated condition, right? So this one that most of you chose was the correct answer, right? Okay, so that was the small quiz there. Okay, well, we can see here again, because these two are significant, so we can see that both. So the target condition was significantly different from the unrelated, and the English competitor was significantly different from the unrelated condition as well. But we're not comparing the whether the difference was larger in one or the other. Okay, so now we can look at the two-way interaction of the condition by poly and the condition by poly 1, condition by poly 1 and the condition by poly 2. And we can see, if you go back to the result, the poly 1 interacted with the condition 1, right? So again, condition 1 was testing the difference between a target and unrelated condition, and poly 1 was a linear term, right? So here we are looking at the interaction between the linear term and the target effect, target versus unrelated condition, right? So we can see that the target and unrelated condition differ in slope, right? And if you look at the graph again, you can actually see the pattern, Right, we had the graph, right? So the fixation function target increases sharply, and it doesn't so much for the analytic condition. The same for native speakers data, right? So that interaction comes from there, right? The time course difference is similar in both groups, right? And so there's no three-way interaction. So this interaction didn't further interact with the Andros group, right? That's what we can see here, right? So this three-way interaction was not significant. Okay. Additionally, there are significant two-way interactions of condition 1 rank 1 and condition 2 rank 1, and three-way interactions of 42 condition 1 rank 1 and 42 condition 2 and rank 1. So 42 here is a quadratic term. So there was a three-way interaction of quadratic term, the condition, the target versus unrelated by language. And that was also the case for the three-way interaction of quadratic term by English versus English competitor versus unrelated condition by language group. We can try and resolve these interactions by running the model separately for each field. Right? So if I run the model for A1 speakers using this command, okay. So what this did is just took out the language factor predictor here, right? And then just took the data from the A1 group, right? So this is just testing the effective condition and its interaction with the polynomials within A1 speakers. So if I get the summary of this model, we have a bit compact fixed effects here, right? So you can see that the condition 1, 2 are still both significant, right? The poly 1, so linear effect by target condition is still significant. The slope was still different with the target and unrelated condition, right? And we can see for poly 2, they both interact. So 42 interacted with the target effect and the English competitor effect in A1 speakers. If we run the same model in A2 speakers, so this time we just changed this group to A2. Nothing else changed in the model. Right. We look at the same fixed effects. We now no longer see the effective condition 2, so there's no difference between the English competitor and unrelated condition. Right. And then we look at the 42 here, we also see somewhat different effects than the A1 speakers data. Like the marginally significant interaction of quadratic term by English competitor effect and a significant interaction of quadratic by target effect. So that's slightly different. A1 speakers data is much more robust compared to the A2 speakers data, especially for 42 by condition 2. So quadratic by English competitor effect. So that explains the interaction. Right, that's sorry, I was able to this bit here, but that was explains. Right. Anything else to add? Right, so that was the bit that I explained. Any question about this bit? Did I miss anything?
I do have a question about the investigating the three-way interaction in this case. Is it also possible to instead of kind of decomposing the model in two separate models per language, to investigate the three-way interaction, for instance, by doing pairwise comparisons using M means or M trends? I don't know if you've worked with those packages. Maybe this is more a general question, but well, first of all, is that possible for this kind of model and data? And perhaps it is, but I'm also maybe curious to see why you do this approach and if there are any pros or cons to either.
Yeah, I actually haven't used the different method means, I guess, but if it's applicable to generalized linear mixed effects model, then that's possible because the base model we are running is just a generalized mixed effects model. So whatever you can do to you can also do so for the gross curve analysis.
Okay. Yeah. Thank you.
Okay. Good. Then shall we move on to the next topic? So we can now look at how we can evaluate the need for the higher order polynomials, right? So I said, like, if you don't really need the higher order terms, you probably don't want to include that in the model because it might overfit the model and it might increase the false positive, right? And so let's check if we need the quadratic over. How we check it, we already know that we do need a quadratic term for A1 data at least. But how we can check that is we can just drop the 42 from the model, right? So let's say I'm just modeling that to just a linear model. So the same model here, but I dropped the 42 from the model. So we're just looking at the interaction of 41 by condition by rank, right? So there's no longer 42 in the model. And we can just run this, right? Then check the model fit, right? So what we notice first is that we now see more linear looking line, and obviously that's because we removed the quadratic term, right? So we no longer try to fit the quadratic or these curve to the data. So that's why the model fit is more linear in this case. And as we've seen that the data looks like this. Right, so we can, if we look at this, we see that these means are often away from the model fit. So that's what we can see that, okay, at least for everyone speakers data, this is not doing a great job in fitting the model to the data. Right, so that's what we can, that's how we can tell that the quadratic sum is necessary for the everyone speakers data at least. Like, maybe not so much for the speakers data. Right, and we can also do a model comparison just to double check. Like, it may not always be the case that this is so clear that we can see this sort of deviation between the model fit and the actual data. Right, so we can just use model comparison that we also use for LME or GLME. Right, so just use the number function to compare two models, and in this case, of course, they define the number of parameters. Or we can use that to check whether the second model with the this one was with the quadratic term was better than the first model without the quadratic model or not, and we can check using the p-value here as well. It's just like the model comparison that you do for LME. So this is another way to check which model is a better fit for your data. Okay,
Yeah.
next.
Oh, Aine, there's a question. Sorry.
Yeah.
Yeah, so I missed it. I should have asked earlier, but you know, when we see an interaction between a term and a condition, does it mean that we are comparing like the condition of interest to the base condition? So the term fits better with the condition of interest than it fits with like the baseline unrelated condition, or?
Yeah, so the condition one is the difference between unrelated and the, what was it? The target. Yeah, so if it's condition one and poly one, and that's significant, that means the slope, linear slope of the target was different from the, Sorry, Aine, is that right?
Yes, thanks, Maki. That's perfect. I couldn't hear the question clearly, so it's great that you answered that.
It was about the interpretation of the interactions. And then, if that also is a three-way with language, that means it's different. Yeah. So it's like
exactly.
Yeah. And this is, I know where, as Breche asked, you can include like not just binary categories like this, but also continuous variables as well, right?
Exactly. Yeah. So you can just add to this module, like as you do here, like you might add, for example, proficiency or something to the predictor here, and then you can use that.
Any other questions? Okay, I think we're good. I know.
Okay, then let's go to the next topic. So we evaluated the need for the high model. So this is just I took from Dan Maman's website and then about how to report the result, right? Because the model output is kind of quite complex, right? So you just, report everything. So this is how the model looks like, and that's a bit too complex otherwise, right? So this is a two rule of thumb that I took from Dan Maman's website. One is to clearly describe each of the three key components of the model. right? So which functional term you used, like did you use the linear term and the quadratic term and the cubic, and so which ones did you include in the model? You need to report that, and what fixed effects, that's also true for any other model, but which effects you included in the model and the random effects, right? You probably already know that these two, that fixed effects and random effects, just as you report for the LME, but for the growth curve analysis, you'd also want to include which functional term you used for your model. Right, so you might, for example, say I included the linear and quadratic terms for my model. Right. Right. And the second thing is for the key findings, report the parameter estimates and standard errors along with significant tests. I mean, if you're familiar with the LMER or G-LaBL, you already know, but basically report the same things like estimate, standard error, and the p-values. Right. Right, and then you can, if you want to look at an example, I put the link here. So you can also check that from the Man's website too. But I skipped that for this tutorial. Okay, then let's go to a quick exercise. So in this tutorial, this is the model that we used, which included the linear and quadratic terms, and this is the one for A1 speakers, right? So this is what we used for the tutorial. And let's assume hypothetically that we have another dependent variable, which is called log fix in this dataset, right? And we don't have that. Let's assume that that's what you have. This is the log transform fixation proportion, right? And you want to test whether this dependent variable is significantly different between the target versus unrelated conditions and between the English completion and unrelated conditions in A1 speakers in the same time window. Okay. Sorry, not the same time window, but time window from minus 800 to 200 milliseconds relative to the target word onset. Okay. You also decide to include a cubic term in the model in addition to the linear and quadratic terms, right? And then the exercise is to write a code to run this analysis. But if you open the tutorial, don't actually run the model here because we don't actually have this variable in our dataset, so it won't run. But just write the code that you would use to run this, and then don't click this one here, but if you have finished writing a code, check here for the solution.
Aine, just letting you know we're working on it in small groups.
Okay, thank you. Yeah. Thank you.
I'll unmute for now.
Sorry, Aine, did you recommend not to try running the code, or can we try, or do you think it'll crash, or is it just impossible to run?
Don't run the code. I mean, we
okay, I won't run
it.
Okay, thank you.
Poly 2?
Yeah, because poly 1 I think makes sense. Okay, slope is steeper.
Yeah.
So does it mean like the peak is higher?
Yeah, exactly. Yeah.
But what if you have like one of the examples here, the peak not necessarily higher, but like later?
Then
Between
you can't. That's not what you can do here.
Okay,
Yeah, it's just about the yeah.
Okay.
Yeah. Yeah, I don't know. Which analysis was that? Aine, there was a question. If you're interested in like kind of poly 2 stuff where you show the peak, but you want to know whether the peak occurs earlier or later for each condition, which would be the best analysis to use?
Right. If you want to know how early the peak is, or
Yeah. So yeah.
Or the difference between two.
Yeah.
Yeah.
How early the effect started to occur, the divergence effect, the divergence point analysis is better. If you just want to know whether the peak differs between the two conditions, then gross carbon analysis can do that.
But does that mean different in terms of how high the peak is? Like so
no, that should appear in the overall difference. So the peak, if you find the difference in the quadratic term, then the curve should be different. So it's not the overall difference. So not the magnitude of the effect.
So if the curve looks like this versus this, like a flatter peak, then that you should detect here, right, Aine?
Yeah. So if you have like two similar looking curves, but one is like more above than the other, then it's not the quadratic term that detects it, but rather the
but if you
difference.
So that's what you say is it could detect if it's like this versus like this.
Yeah, okay.
Then you can detect it. Yeah.
But it would not detect then if it's kind of the same shape, but it just happens later in one condition than in the other. That you wouldn't get that from poly 2.
I don't think so. I know, right? So if the curve shape is the same, but it happens earlier or later, that will still be non-significant for here, even if you. So if you're looking at when the peak occurs, basically.
Yes, that might actually be rejected by point two, because if one peak occurs here, the other occurs here, then that can be rejected.
Yeah, so then you would use divergence point analysis or something like that.
No, I think
that would help you detect when these effects started to occur. So
yeah, you said it wouldn't maybe detect, right? If it's the same pattern, but it appears earlier or later, that would.
Sorry, I said it does. It does.
It does.
Yeah, so it might detect because the curvature pattern might be different. So it's like starts with the clear peak and then decrease gradually towards the end. Let's say that's the pattern, and the other pattern is kind of start slowly and then increases sharply and then goes down. And if that's like kind of two different peaks, that can be detected using the polynomial here. So the quadratic terms here.
Okay.
But we don't know how fast the effect will get for one condition.
I see. Yeah, I guess it all depends on the pattern of the curve. So
yeah, I just wonder like how big the difference has to be before.
That's an empirical question, I guess. How's everybody looking? So good. Maybe 3 or 4 minutes more, Aine, and then.
Sounds good.
Okay, I think most of us are done.
Okay. Then, yeah, so if you have written this and click on the solution, you can see the solution here. So maybe perhaps go to the solution tab to say which one you should have changed to run this code. But again, we collect solution here. So first, you want to change the time window. So the original data used as from -800 milliseconds to 0. So you have changed the time from -800 to 200 milliseconds. And then now that you want the cubic term, so you change the Fourier order. I set Fourier order to 2 to include the linear and quadratic terms. But if you want to include the cubic term, you set this to 3 to include all three, so linear, quadratic, and cubic. And then you, of course, want to put the cubic term in the model as well. So change the model syntax to 41, 42, 43 instead of 41 plus 42. Right. And then obviously, actually I said this here, but let me come back to that in the last point. So you change the GLMER to LMER because this log, what was it that I said? Log ratio. Yeah, log transform fixation proportion. So now it's a log. It's no longer a binomial value. So you want to drop family equal binomial from your model and change it to linear because again, you're no longer modeling binomial dependent variable. And then finally, of course, change the dependent variable to log fix from count. Okay, so if you have changed all that, you should have got what is written in the solution here. Okay. Any question about the exercise?
Did we all get it? Looks like it.
Okay, great. Yeah, that was all for the growth curve analysis and looking at the time. I probably don't have time to look at the cluster validation today. Probably.
Yeah, I think
yeah.
So it's 12 and we have another.
So tomorrow.
Yeah. So maybe we could leave it for now today, and then tomorrow we'll do the other 4 analysis, the same kind of structure, I guess, Aine, right?
Yeah, yes.
Okay. So perfect. Thank you, Aine. So let's give her a round of applause.
Thank you.
Great. Okay, so then if you weren't able to download anything, I'll stay on here for a little bit so you can ask me or Aine. Maybe Aine, you can stay a little bit.
Sure.
And yeah, and then we'll see you tomorrow, same time, 9 a.m. And if in the meantime, if you have any questions, let me know. But yeah, thank you, and I'll see you guys tomorrow. Okay, bye.
Thank you.
Oh, and I'll stop. Aineちゃん、ちょっと待ってね。Stop recording.